Okay, we are going to start this time another series of lectures because the topic which we are covering this time cannot be covered in one session or one video lecture or one PPT. So the topic is hashing, right? So we will have 2 or 3 lectures on that. Now hashing, basically the purpose of hashing is to perform all the dictionary operations in order of one time. Now what do we mean by dictionary operations? The operation insert, delete, search, update. These 4 operations are the commonly used operation on almost every data structure, you name it. For example, you have an array, you have a linked list, you have a tree, you have a stack. For example, you have a stack or you have a queue. These are just a few data structures, but there can be many. So these insert, delete, search and update operations are almost performed on every data structure. So the purpose of hashing is to make sure or is to achieve the target of executing these dictionary operations in order of one time, right? So but before going into the details of hashing, we need to understand another concept, which is the direct addressing concept. But rather, let me follow the sequence of slides. So many applications require dynamic set of support dynamic set that support dictionary operations, which are insert, delete, search and update. For example, a compiler maintaining a symbol table where keys correspond to identifiers. Now this, let me explain it to you. Symbol table, when you write a code in your program, for example int z is equal to 3, so the compiler maintains a symbol table where uh, it it is a table which keeps the record of the variables which are stored in the which are used in the program. For example, z is a variable, it has a column which stores the names of the variables, then the type of the variable, right, and then the value of the variable, so on and so forth, right? So compiler needs to access this symbol table back and forth multiple times. So these dictionary operations are very frequently performed on this symbol table in the context of a compiler, whether it be a compiler of C++ or Java or Pascal or whatever. So the symbol table needs to be stored in a place or in a data structure which is quick enough, and the operations should be such that they are performed in order of one time, so that the delays can be minimized. But this is true for any other domain as well. For this, hashing is a good data structure for implementing the dictionary operations. Although searching can take as long as linked list, in worst case that is order of n in terms of hashing, but how it will be taking, I will be explaining it shortly. But with reasonable assumption, all the dictionary operations in the hashing consumes order of one time, right? Uh, The hash table is generalization of an ordinary array with direct addressing taking order of one time. Now, instead of reading out these things, let me explain to you a scenario, and there I'll be explaining it, the hashing. But before that, there is another concept which is called the direct addressing table, right? So, okay. Now, So direct addressing is a concept where we have a universe of keys. Now, to give you an example, for example, there is a university which is named as, for example, GIK Institute, right? So that university admits, let's say, for example, in the year 2020, the university admitted, for example, 1000 students in the institute, right? So and the university wants to keep record of these 1000 students in some data structure, so that if you want to insert the student, insert the record of a student in the data structure, if you want to delete the record of the student, we want to update the record of the student, if you want to search the record of the student, all the operations should take order of one time, right? Now okay, now what will happen is, in the direct addressing, we will make an array with 1000 slots. For example, slot number 0, slot number 1, slot number 2, slot number 3, slot number 4, up till 1000, right? Now, if a student comes and his ID is his registration ID is, let's say, 2000 dash, let's say, 4. So this 2000 signifies the registration year, so this is the actual ID. So what we will do, we will insert the record of this student in 4th slot, right? So the insertion operation, right, this insertion operation is executed in order of one time, right? If you want to delete a record, we will straight away go to the slot number 4 and we will delete the record, right? So this operation also performs in order of 1. If you want to search, we will simply go to slot number 4 and we will see if there is a value. It means the value, the student information is stored there. Otherwise null will be placed here. So this is also in order of order of 1. And if you want to update, we simply go to this cell and we can update the information. This also happens in order of 1. Now this may happen that within this cell there is a pointer to a structure, and the structure contains multiple variables. For example, name of the student, age of the student, CGP of the student's address, so on and so forth. That can happen, but again, that is only one cell ahead, so it is as good as taking order of one time. Now this is the concept of direct addressing, but there is a catch. Now if we see here, this blue, rather I've made it blue now, this 1000 is this universe of keys. This is the actual universe of keys. Let's suppose if 1000 students gets admitted to the institute and we declare an array of 1000, but let's suppose after a week or so, only out of 1000, only 700 students remain in the institute. So in that particular case, 300 slots in this particular array will be free, or we can rather say the proper word is unused. So 300 slots will be unused in this direct addressing table, right? So this is the concept of direct addressing table. Now there is an advantage, there is a limitation of the direct addressing table, is that when the actual number of keys which are to be stored in the direct addressing table are very much less than the actual universe of keys, then the direct addressing table is not suitable. For example, to give you an example, for example, for a problem statement, we have let's say for example, we have 100 universe of keys. I'll be demonstrating it shortly using a different example as well, but for the sake of completeness, let us consider for a scenario, for a particular scenario, in the universe of keys we have 100 keys, right? By key I mean a primary value. For example, your CNAC number is your key, which is a unique value in the complete country. In the context of a university or a school or a college, your registration number or your roll number is your key, right? So in the universe of keys, for example, we have 100 keys, but the actual keys which are to be stored are, let's say, 5. So here the difference between the universe of keys and the actual keys is huge. Like 95% of the keys which were in the universe of keys are not going to be stored in the actual keys. So in this particular case, this direct addressing table is not a good solution, right? So direct addressing table is good when the difference between the universe of keys and the actual keys is less. One. Secondly, at times the value or the number of universe of keys is too large that a direct addressing table cannot be created and cannot be stored in the memory. So that is also a limitation. For example, if you want to store the CNIC numbers of every person in Pakistan in a direct addressing table, then we will have to make a very large direct addressing table which is not going to be fit in the computer's RAM. So direct addressing table is not a good solution here. So in the direct addressing table, the range of keys is from 0 to m minus 1, where m is the size of the direct addressing table. Keys are distinct, we already know, and and all the operations, as I would earlier explained to you, takes order of n time, right? Here when I upload the slides, you will have a particular slide named as table. It will explain what a table is, but a table is simply an array, right? The array is also called a table. This is 1D array, and the 2D array can be like this, right? So this is called a table. It's a name value pair where k is the index of the array and I is the information stored in that particular cell, right? Now the direct addressing and remember, this direct addressing table is not actually hashing, right? So this is a topic which is a prerequisite of hashing. So direct addressing is actually not hashing, right? I'll be explaining hashing maybe in this lecture or maybe the next one. So if you see here, this is here the problem is shown pictorially, and if you see here, this oval, this pink sort of oval shows the universe of keys, but this blue oval shows the actual keys which are to be stored. Now and this is a direct addressing table, basically a 1D array. Here this is cell 0, cell 1, cell 2, cell 3, 4, 5, 6, 7, 8 and 9. And when we have to store key number 2, we directly go to the slot number 2 and store it here, right? Here it may the pointer may be stored, and the pointer may point to a node or a structure or whatever where the actual value is stored. So if you see here, the insertion, deletion, update, searching, all the operations are performed in order of one time, right? So you don't need to have a big of hassle, but there are advantages and limitations of the direct addressing table. Direct addressing table is most efficient way to access the data, since it takes only a single step for any operation on direct addressing table. It works well when the universe of keys is reasonably small. By reasonably small, we mean that it should get it should get accommodated in the RAM. But there are difficulties as well in case of the direct addressing table, uh, and the first difficulty is that uh, storing a table T of size U may be impractical, because if the size is very large, it cannot be stored. The set K of keys actually stored may not be relevant to you. The most of the space relative to you, sorry, most of the space allocated for T may be wasted. For example, if the set U is very large than set K, then most of the space is simply going to be wasted in case of direct addressing table. So let us understand this by a simple example. For example, we have a table of 50 students in a class, and each student is represented by a SSN, social security number, which has 9 digits. It means that it will have 1, 2, 3, 4, 5, 6, 7, 8 and 9 digits. Now each digit can have either, here we can have either 0, or we can have 1, we can have 2, up to 9, right? So here we have a possibility of 10 different numbers, digits can appear here, and in total we have 9 slots. So it means that and we have how many students? We have 50 students. So if we want to have unique SSN numbers for every student, then we have 10 raised to power 9 possible SSNs. We have 10 raised to power 9 possible social security numbers. Out of these 10 raised to power 9 social security numbers, we are going to save or store only 50 social security numbers in our direct address table. It means that only 0.000005% of the social security numbers are going to be stored, and 99.99995% of the space is going to be wasted, provided we opt for the direct addressing table, right? So that is a limitation of the direct addressing table, but it has got its own advantages as well. So to overcome this limitation, the idea is to have a table of very small and fixed size, and there the concept of hashing is introduced to overcome this limitation. Instead of covering this hashing in this lecture, I will stop it here, and we will cover this hashing, and there are a lot of other details in hashing as well. We will cover this in next couple of lectures. Thank you.